we're now in a position where we can use total dual integrality. And we're going to circle back to an earlier lecture where we talked about the r-Arborescence problem. So I'll restate here the definition of that before we go on to give the main result, which is that the LP relaxation of the r-Arborescence problem is exact. In other words, it's integral. We can drop the integrality constraints. So our starting point is a directed graph. So now E is a set of directed edges. And the r-Arborescence problem has a special node called the root. So R is in V, and we call this the root. And an r-Arborescence, a set of edges, is called an r-Arborescence if every node that's not R has exactly one edge or one arc. I guess sometimes in terms of the jargon, you'll see arc is a directed edge. I guess I'll be a little bit loose and use both here. But I really mean directed edges now that we're in the context of a directed graph. It has exactly one arc terminating or pointing to in V. So what that picture is really saying is that if this is R and this is my graph, my directed graph, like I said, I always get carried away when I start drawing graphs. I just want a simple idea here. And so an arborescence for this graph, if this is R, would be this collection of nodes. And you can see that it satisfies this property. So one way to simply categorize it in your mind is think of this as a spanning tree. So this is what an r-Arborescence is. And the problem of finding a minimum length arborescence comes whenever we have a length function on the edges. So if each edge E has a length LE, which is assumed to be non-negative, then the min length r-Arborescence problem is to find an r-Arborescence of a minimum length. Is to find, I guess that's as circular as it gets, to find a min length r-Arborescence. And if you recall, one of the key properties that we had defined and which allowed us to write down the main constraints that we needed for the integer programming formulation of the r-Arborescence problem was this relationship to cuts. And the fact that the minimum length of an r-Arborescence is equal to the maximum number of R cuts. So we had used that result in order to write down the Min Arborescence problem, but we can now generalize this as follows. So we have this the following theorem tells us that the min length of an r-Arborescence when arc or edge E has length LE is in fact equal to the maximum number of R cuts C1 to CT. And recall that a cut is, for r-Arborescence, is defined as the edges that cross over into any subset of the nodes that does not include R. So in other words, a cut is a set of edges that separates R from some portion of the graph, such that no arc or edge E is in more than L of E cuts. Okay, so now let's remember what our LP formulation was of the r-Arborescence problem. Okay, so to form this LP relaxation, let's define a matrix C as follows. Remember, our constraints are going to be as follows. So I'm going to define C so that, similarly to our incidence matrix of a graph that we saw for max flow, and we saw also for bipartite matching, we're going to index the columns by edges. So these are indexed by edges or arcs, but the rows are not going to be indexed by vertices, but rather they're going to be indexed by cuts. So every row corresponds, this row corresponds to a subset U of the nodes that defines a cut. And remember that any subset of the nodes that doesn't contain R defines a cut. So there's lots of these. So this matrix C, and if you look back to the lecture where we introduced r-Arborescences and I wrote down the LP problem then, we had an exponential number of constraints. So in other words, all we need is that U is not empty, and it is any subset of V, but not including R. And so then the Min Arborescence problem is the following. Min, if L is my length function, and X is my variable on each edge or each arc, it's min L transpose X such that Cx is greater than or equal to 1, and X is greater than or equal to 0, and each XE is either selected or it is not selected. So this is the exact reformulation of the r-Arborescence problem, and we had discussed this more in depth when we first introduced this, and we first introduced the relationship between R cuts and r-Arborescences. So I'm not going to go over all of that here. The LP relaxation we get by crossing this out. So this is now an LP, admittedly with exponentially many extreme points. Another thing that we had shown in the first lectures on r-Arborescences is that even though there are exponentially many extreme points, we have an efficient way to implement a separation oracle. And in fact, our separation oracle comes from solving a max flow problem, or in fact, a collection of max flow problems. And that is what motivated all the lectures on ellipsoid algorithm. So we're not going to get into all of that now. I'm just recalling what is the LP. And therefore I can write its dual. So the dual of this is maximize 1. And here actually I really should be more careful. I should be calling this 1. This is a vector, that's all ones for every single non-empty subset that does not contain R. That's because that's what every single row of C corresponds to. The dual is maximizing this vector transpose Y. Y will be my dual variable, subject to Y transpose C less than or equal to the objective function, L, and Y non-negative. So this is the dual. So the main result is the following. Both of these linear programs are integral. Both primal and dual have not just integral values, but integral optimal solutions for any vector of lengths that are non-negative. So I'll denote it in this way. So for any vector of non-negative integers on the edges, corresponding to the edges, that defines the objective function for the r-Arborescence problem and therefore the constraint for the dual. Both of these problems are integral. And that is essentially what we want to show. And from this integrality, you can also conclude the previous theorem. Okay, so now enter total dual integrality. So what is it enough for us to show? Total dual integrality says that to prove this theorem, it is enough to show that this max here on the right-hand side has an integral optimal solution. So I'll squeeze this in here. To prove the theorem, basically by all our work on TDI on the previous lectures, it's enough. Well, let me write it in that way. Rather than saying by TDI, I'm just going to say to prove the theorem, we show system is totally dual integral. And what does that mean? It means that all I need to do is, not that this is a small task, I need to show that this right-hand side has an integral solution. So we must show the max has an integral solution whenever it is finite. So this is what we're going to do. Actually, let me squeeze one more thing in. It has an integral solution for every L. Now note one point here. If you recall TDI, I needed to show that the dual has an integral solution for every integral C. But this theorem is only only claiming something is true for every L that's positive. This is actually a very easy bridge to cross, because you can easily see that if we do have negative values then the dual is going to be infeasible. So if you look at the primal, if L has some negative values, there is nothing in the constraints that we've written that stop X from taking an arbitrarily large value. So the primal would be unbounded, the dual would be infeasible. And that's why it's enough to show. Remember, the TDI result is only required us to show integrality whenever their strong duality holds. So this is the bridge between showing something for every L that's integral versus for every L that is a non-negative integral. Okay, so let's launch into this proof, and one of the important aspects of this proof is that it's going to give us this opportunity to talk about this concept of laminarity that I want to introduce. And the proof, the proof relies on this idea of laminarity. But again, laminarity is much more important. So I'm going to take this opportunity to define this. So a collection of sets, a collection of subsets of some base set, of whatever, of anything. I'll just use S as a generic set of discrete set of elements, is called laminar if it has a property that whenever U1 and U2 are subsets that belong to F, then one of three things must happen. Either U1 is a subset of U2, or U2 is a subset of U1, or U1 and U2 don't intersect at all. So let me just draw a picture. Let me. So what this is saying is that, if I have a collection of subsets, U1 and U2, or what does my set F look like? It has a collection of subsets. Is this allowed? Yes, it's allowed because they're nested. I can nest further. Is this allowed? Yes, because any two of these subsets are either nested or they have no intersection. And again, that means I can add. Okay, so here's an example of laminar sets. So basically you either have nestings or things are disjoint. What you are not allowed to have is something like this. So that's not allowed. Okay, so this is the definition of laminarity. Okay, so now we're gonna use this in an important way. Again, laminarity is broadly an important property. So let's look at this. This maximization problem is going to be something that we're going to use a lot. This is what we're focusing on for total dual integrality. Okay, so let's let me paste this back in here. Okay, so let me call this star. This is my maximization problem, and let's take an optimal solution. Possibly there are many optimal solutions. So let's first we're assuming that L is positive, so that everything is finite. You can also see from the way that the objective is defined. Let me just flip back so you can see the minimization problem. When you look at this minimization problem, it's clearly feasible. How can we tell that it's feasible? Just take every edge in there. If you take every single edge in there, clearly this is feasible. Of course, that's not an optimal solution. So we know that the primal is feasible. But if L has no negative values, since X is bounded from below, we know that the smallest this min can be is 0. Once you have something that's feasible and bounded, you know that strong duality holds. Okay, so for the duration, we don't need to discuss that more. That means that without further thought, both problems are feasible. Both primal and dual are feasible. Both primal and dual have finite optimal values. We get this immediately from duality, weak duality, in fact. So let's let Y be a maximizer of star. But in particular, I'm going to choose a specific maximizer because there might be multiple. And if there are, if we have multiple maximizers, then choose the one that makes an additional objective function as large as possible. So choose the one that makes this sum, yu times u squared, as large as possible. All right? If there's a unique one, we don't have to worry about it. But if there are two or more, I just look at all different y's, and I am going to pick the one that that maximizes this quantity. So again, this is not a multi-criterion optimization problem. I'm just first finding the maximizer. I care about the maximizer, and then I'm going to pick the solution that maximizes this. So the first lemma, actually, let me just call this a claim, is that if I look at the set F, which is all u for which y is positive. In other words, I'm just looking at the support of y. That this set is laminar. This, by the way, is a very common technique for extracting, if there are multiple solutions, extracting one which is laminar. We're not going to prove this claim right now, but it is it takes a little bit of thought, but it is straightforward in a way that this that picking something that minimizes this kind of objective would give you something laminar, because it's basically saying, again, I'm just kind of hand waving my way here. I don't want to go into the proof, but it's basically saying that if you do have two sets u like this, and certainly those sets are not disallowed by the optimization problem, y could have support on those. From those, you can if the optimal solution that you've chosen has support on two y's that correspond to two u's that have an intersection, you can find a different y where you can show that it's also an optimal solution, yet one which makes this even bigger. Okay, so but I won't go. We won't prove this. We won't prove this this claim right now. So now what are we going to do? Now I'm going to let, given this laminar family F, remember what is this? What is C? The rows of C correspond to the rows of U, and therefore I'm going to pick a subset of those rows. I'm going to call that C dash, which I don't want to confuse with C transpose. So let's C dash be the submatrix of C with rows corresponding only to those subsets U that happen to belong to this laminar family F. So this is C dash. I'm throwing away any row that doesn't correspond to something in F. So my next important claim says the following. It says if I look at my primal objective function and I only look at C dash, I don't change the value. So the claim is if I look at the problem, maximize, excuse me, I'm looking at the maximization, I'm not looking at the primal. Subject to y transpose C less than L transpose y non-negative. This is my original maximization, what we called star on this slide. The claim is that this is equal to the problem of maximizing 1 transpose y subject to y transpose C dash less than L y non-negative. So let's prove this. Let's prove this claim. So one direction is immediate. So what have we done here? Note, I have thrown out rows. Rows in the primal correspond to constraints, but rows in the dual help us. They give us more power. So the fact that in the inequality that this inequality is immediate. You can also think about this through a duality perspective. Rows in the primal make my life harder because there are additional constraints. The primal is a minimization problem, therefore adding constraints increases because I'm trying to minimize and make my life harder. It increases, and that's another way to see that this inequality is it holds in the dual as well, since we have strong duality. So more rows means primal and dual, therefore increase. Okay, but what's going to give us the reverse inequality is that the maximizer of the right-hand side is easily obtained from the assumed maximizer of the left-hand side. So this is also easy. I won't write down that it's easy. I'll just say it follows because we already have a maximizer of the left-hand side that has zeros for all rows not in C dash. Remember, when I'm left multiplying a matrix, I'm combining its rows. When I'm multiplying, when I have AX, X is just taking a linear combination of the columns. Now, Y transpose C takes a linear combination of the rows. But if Y has zeros on the left-hand side here on all of the rows that are not in C dash, then Y transpose C, then I can just take that Y and easily get a solution in my other problem, just by throwing away those zeros. Okay, so these are equivalent. So that means that instead of star, I can just focus on this one. So let's call this star star. And so if I can show that if I have an integral solution to star star, then I have an integral solution to star. I get that just by padding zeros, because we know that that it'll be optimal. We know that by padding zeros, I get something that again is feasible. And that is exactly what we want to show. We'll have concluded that we have a TDI system. So here is the key claim. Now that we've thrown away all of the rows except for those that correspond to a laminar set, we have the magic, which is that now this new matrix, C dash, is totally unimodular. And as soon as I have total unimodularity, we have, so once we prove this claim, so this claim implies that optimization star star has an integral solution. But then by the previous claim on equality of star and star star, and because a solution to star star can be padded with zeros, it can be made into a solution to star that's integral by padding with zeros. This implies that we have a TDI system, which is the end of the theorem. So we have an important claim that we still need to prove. And we're going to do this in the next lecture.